Hi, hello everyone. Today we are going to learn about electromagnetism from physics from 5 chapter 3. This is one of the important and interesting topics from 5 physics. Let's learn about it. First of all, the definition of electromagnetism. When a current passes through a conductor, magnetic field will be generated around the conductor and the conductor will become a magnet. This phenomena is called electromagnetism. Okay, when a current passes through a conductor, okay, let's assume this is a straight wire and this is the direction of the current. When the current passes through this conductor, a magnetic field will be generated along the conductor, and this incident, this is called electromagnetism. Okay, in SPM we need to know the magnetic effect of the following current carrying conductor, which is straight wire, coil and solenoid. Okay, these are the syllabus of SPM physics topic. So these three aspects are important and will ask in SPM questions. Okay, first one, straight wire. Okay, this rule is very important. Right hand grip rule. We use this rule to determine the direction of magnetic field. Okay, as we know the direction of current. Okay, this will be the position of our right hand grip rule. Okay, the thumb here is represent the direction of current and the grip represent the direction of magnetic field. Okay, let's see the picture on the right hand side. Okay, two circles. Okay, a circle with a dot shows that the current is coming out from the plane, which means the current is coming out from the plane. Okay, let's be applying the right hand grip rule. The thumb will be pointing toward us and the grip will be anti-clockwise. Okay, remember, when it's a dot it should be anti-clockwise. Okay, and the cross shows that the current is moving into the plane. Okay, as we are applying the right hand grip rule, the thumb will be pointing to the plane and the grip will be clockwise. If cross, it's moving clockwise. Okay, let's go for the coil or circular loop. The thing is same. Okay, what the difference is, the direction of current flowing at the left hand side is on the top and the right hand side is flowing downwards. Okay, which means the direction of current is different at the left hand side and right hand side, so it will create the magnetic field in the different direction too. Okay, so that's why the left hand side will be rotating anti-clockwise and the right hand side will be rotating clockwise. So this is the difference between straight wire and the coil. Okay, the factor that affecting the strength of magnetic field. Okay, first one, increase the current. Okay, let's see one with current 1 ampere, another one with 2. Okay, the higher the amount of current, the higher the strength of magnetic field. Okay, the second point is increase the number of turns of coil. Okay, let's see a turn one turn of coil, another one is 2. Okay, the higher the amount of coil, higher the number of turns of coil, the higher the strength of magnetic field. The third point is the radius of the coil. Smaller one, higher one. Which one has a higher electromagnetic strength? Okay, both are applying with the same amount of current, so the one with smaller radius will generate a more strengthful electromagnetic field. Okay, let's go for solenoid. What does solenoid means? Okay, solenoid is a long coil made up of a number of turns of wire. Okay, this is the solenoid. Okay, let's see the picture on the left hand side. Okay, so here, okay, the current is coming out from the plane, so which means it's a dot here. Okay, it's a dot means it will be rotating counterclockwise, anti-clockwise. So here the current is going into the plane, which means it is a cross, and the rotation will be clockwise. And for this solenoid we apply the right hand grip rule. Okay, here the grip represents the current, and the thumb represent the north pole. Okay, so at here north pole, the magnetic field is starting to generate from here, from north pole to south pole. Okay, it's still applied with the magnetic field and the current, but here we change the current as a grip and the thumb as the magnetic field, which determining the north pole. For solenoid we apply the right hand grip rule to determine the north pole or south pole. Okay, this picture here shows the observer from different side. Okay, how they are determining the poles of the solenoid. Okay, so the observer at the left hand side, okay, the direction of the current will be clockwise. So if clockwise means, okay, it's a south pole. Okay, the observer at the right hand side, he or she see that the current flowing, the direction of current flow is anti-clockwise. So anti-clockwise means it's a north pole. Okay, the strength of the magnetic field. The strength of magnetic field can be increased by increasing the current, same as what we have learned from the coil. Okay, increase the number of turns per unit length of the solenoid. Okay, same also. And using a soft iron core with the solenoid. Okay, solenoid is it's in cylindrical shape and the center is empty. Okay, so when we insert a soft iron core, as we are inserting the soft iron core inside the solenoid, so the magnetic field will be more strength. Okay, now we are going to learn about the force on a current carrying conductor in a magnetic field. Okay, in this subtopic we will learn about Fleming left hand rule. Okay, this is the Fleming left hand rule. Okay, we apply this rule to determine the direction of force. Okay, let's see the picture on the top. Okay, and here the current is flowing from top to bottom, and this is the direction of the field. So now we have to determine the direction of force applying Fleming left hand rule. Okay, so our first finger will be pointing the direction of magnetic field. So here will be the direction, we have to point our first finger here from north pole to south pole, and second finger the direction of current. Okay, so second finger have to pointing downward. Okay, so where will be our third finger? The thumb will be pointing the direction of the force. Okay, the thumb will be pointing towards out. Okay, which means, okay, it's a dot as we are viewing from here. So it's a dot coming from the plane. So this is how to apply the Fleming left hand rule to determine the direction of the force. Okay, direction of force determined by using Fleming left hand rule as we did for the previous example. Okay, so the thumb represent the force, the first finger represent the direction of magnetic field, and the second finger represent the direction of current. Don't get confused which finger represent which one. Okay, so these are the keywords. It will be easy to remember. So the second finger C, which means current, the first finger F means magnetic field, and the thumb means M, motion. Okay, now we learn about the catapult field. What does the catapult field means? Okay, the interaction of two magnetic fields, okay, that produce a result field known as catapult field. Okay, the interaction with two magnetic field. Okay, the picture on the left hand side shows the result when there's a interaction between a permanent magnet and a current carrying conductor, electromagnetic field. Okay, the picture on the right hand side shows the clear picture. Okay, a permanent magnet react with a temporary magnet, so this shows the result. So this is the catapult effect or the catapult field. Okay, the resultant force is acting downward by applying Fleming left hand rule. Okay, the thumb to determine the force and the cross here showing where the current flows. Okay, so our second finger should pointing in, and our first finger to point the direction of magnetic field. Okay. The turning effect of a current carrying coil in a magnetic field. Okay, how can a turning effect occur in a current carrying coil? Okay, when there's a force acting, okay, by applying Fleming left hand rule, we know that there's a force is acting, generating when there's a reaction between a magnetic field and a current carrying conductor, which produces an electromagnetic field. Okay, so by applying Fleming left hand rule, we know, okay, at the picture here, the direction of magnetic field should be north pole to south pole. Okay, so here the current, we know the direction of the current. Okay, let's determine for the right hand side here. So our second finger should pointing toward us, and our first finger should point toward to the left, and our thumb will be pointing downward. Same applies for the left hand side. Okay, so this is the result. A permanent magnet where there is two temporary magnets, okay, and left hand side and right hand side, both are in different directions. So this will produce, this is the result, and this is known as the catapult field. This sketching is more important. Okay, so there's possibility in asking SPM questions, and past year question they do ask about this, so try to practice, do more sketch about this. Okay, now we are going to learn about electromagnetic induction, one of the important subtopic, and student don't get confused with electromagnetic and electromagnetic induction. Okay, let's learn about more detail. Okay, Lenz's law. Lenz's law stated that the induced current always follows in the direction that opposes the change in magnetic flux. Okay, this Lenz's law obeys the principle of conservation of energy, which means the kinetic energy, okay, before and after is it same. So that's the principle of conservation of energy. Okay, Faraday's law. Faraday's law stated that the magnitude of EMF, electromagnetic force, induced in a conductor is directly proportional. The induced EMF, the magnitude of induced EMF is directly proportional to the rate at which the conductor cut the magnetic flux. Okay, so these two laws are important, Faraday's law and Lenz's law. So this telling about electromagnetic induction. Okay, now we learn about Fleming right hand rule. Okay, don't get confused with Fleming left hand rule and Fleming right hand rule. Okay, for Fleming left hand rule, we usually use that to determine the direction of the force, and for Fleming right hand rule, we always apply to determine the direction of induced current. okay, as the thumb is still representing the motion. Okay, first finger representing the magnetic field, same as left hand rule. Okay, and the second finger is representing induced current. Okay, this is the differences between Fleming left hand rule and Fleming right hand rule. Okay, Fleming left hand rule, okay, we use to determine the direction of the force that moves the wire to conduct current in a magnetic field. For Fleming right hand rule, it used to determine the direction of induced current that flows from the wire when there is relative motion with respect to the magnetic field. Okay, Fleming left hand rule, the magnetic field and current we know, and we have to determine the force. Okay, for Fleming right hand rule, the magnetic field and force we have known, and we have to determine the current. Okay, for the Fleming left hand rule, electrical energy, the kinetic energy. Right hand rule, kinetic energy produce electrical energy. Okay, so by knowing the application of Fleming right hand rule, I hope you can get a clear picture about what is mean of electromagnetic induction. Okay, now we learn about direct current generator, DC current. Okay, DC is an electrical current in which the direction of the flow of the electron is in one fixed direction. Okay, for direct current, so it has coil, commutator, carbon brush, galvanometer. Okay, this is the preparation for the direct current generator. Okay, for the AC current, it is an electric current in which the direction of the flow of the electrons is changing with time. Okay, that is the difference between DC current and AC current. Okay, for DC direct current, the direction of the flow of the electron is same, is constant, one fixed one with time. Okay, for AC it's changing with time, and the setup will be like this. It has coil, slip rings, carbon brush, and galvanometer. Okay, factors that affecting the magnitude of induced EMF. Okay, the strength of magnetic field, as higher the magnetic field, so higher the EMF. Okay, the number of turns of coil, higher the number of turns of coil, higher the magnitude of EMF. Okay, presence of iron core in the coil. Okay, as there is an iron core in the coil, so it generates a more strength electromagnetic field, and it will increase the magnitude of induced EMF. The speed of rotation, higher the speed of rotation, higher the strength of magnitude of induced EMF, and the area of the coil. Smaller the area of the coil, higher the magnitude of induced EMF. Okay, this is the difference between DC and AC. Okay, I hope this graph, by comparing this graph, you can get a clear picture. Okay, where for DC the current is constant at time, and for AC it's changing with time. Okay, so this table, effect on a bulb, effect on a capacitor, effect on moving coil, loudspeaker. So this, when we're doing the experiment in the lab, so this is the effect and this is the result. So you can differentiate AC and DC by comparing their results. Okay, now we learn about transformer. There's two type of transformer. One is step up transformer, another one is step down transformer. Okay, step up transformer means it receives a smaller amount of current and it produces a higher amount of voltage. And for step down from higher, the result will be lower. As seeing this picture, by seeing the number of turns of coil, okay, we can determine whether this is a step up transformer or a step down transformer. Okay, we learn about it in more detail. Okay, these are the calculation formula that we have to use for the step down and step up transformer. Okay, the calculation of potential difference change. Okay, Vs over Ns is equal to Vp over Np. This is the formula, where P means primary and S means secondary. Okay, the voltage over number of turns and the voltage over number of turns. Okay, calculation of current change. Okay, ideal transformer. Okay, Is Vs is equal to Ip Vp. Okay, also you can say as Vs over Vp is equal to Is over Ip. Okay, for non-ideal transformer, to find the efficiency, so formula is Is Vs over Ip Vp times 100, or P output over P input times with 100. So these are the formulas, the important formulas that we have to use to find to calculate potential difference, the current change in ideal transformer and non-ideal transformers. Okay, the factor that affect the efficiency. Okay, these are the four factors. The heating effect on a current in a coil, okay, that will affect the efficiency. The heating effect of induced eddy current, okay, the magnetization of the iron core, and flux leakage. These are the four factors that affect the efficiency of a transformer. Well, that's all about this topic, electromagnetic. Okay, I hope you all can understand what I've teach you in this video. So if you have any doubt regarding this topic, you can ask in the comment section below. I just mainly focus on the calculations part. Okay, I skip some of the applications of electromagnetic in our daily life, so you can refer your textbook to know in more detail. And if you have any doubt, you can ask in the comment section below. We will reply to you as soon as possible. And if you find this video is useful, share with your friends. So good luck for your exam and thank you.